At first, the Atlantic looked protected. El Niño was supposed to weaken the season, tear storms apart with wind shear, and keep the worst hurricanes from organizing. But while one basin stayed quiet, another ocean began moving. Off Mexico and Central America, warm water, slow-moving lows, and tropical rain bands started lining up against steep terrain. The danger was not the monster hurricane people were warned about. It was quieter, wetter, and easier to underestimate. So, what happens when the shield works in one place but fails in another? And what threat is hiding behind the calm Atlantic map now? The forecast that did not match the ocean. At 2 o'clock in the afternoon, Eastern Daylight Time on Sunday, June 7, 2026, the Atlantic Basin looked almost empty. The National Hurricane Center in Miami had issued its tropical weather outlook for the North Atlantic, the Caribbean Sea, and the Gulf of America. The sentence was short, and because it was short, it mattered. Tropical cyclone formation was not expected during the next 7 days. That was the official Atlantic picture. No named storm, no tropical depression, no developing hurricane, no Category 4 forecast inside 72 hours. The basin that absorbs most of the public fear each June was quiet, but the quiet was not safe. Far to the southwest, on the Pacific side of Mexico, the satellite image was beginning to show a different atmosphere. The water off Guerrero and Oaxaca was warm, dark, and unstable. Bands of heavy showers were already reaching the coast. Beneath those bands, a weak center of circulation had become defined enough for the National Hurricane Center to classify the system as Tropical Depression 2E. At 3 o'clock Central Standard Time, its center was near 15.7 degrees north and 99.7 degrees west, about 85 miles south of Acapulco, with maximum sustained winds near 35 miles per hour. That number does not sound dramatic. 35 miles per hour is below tropical storm strength. It is nowhere near hurricane strength. It is very far from Category 4, which begins at 130 miles per hour on the Saffir-Simpson scale. That detail matters. The danger in this first chapter is not a hidden Category 4 storm. The danger is the wrong threshold. The cyclone near Mexico was not forecast to explode into a major hurricane before landfall. The official forecast showed moderate strengthening, likely to tropical storm strength, before the center moved inland, weakened, and dissipated within 48 hours. In wind terms, this was not the storm in the headline. In water terms, it was already serious. The warning area stretched from Laguna de Chacagua to Tecpan de Galeana. Along that coastline, tropical storm conditions were expected within 24 hours. Rainfall totals of 4 to 10 inches were forecast across coastal portions of Guerrero and Oaxaca, with isolated maximum totals near 12 inches. The National Hurricane Center used the phrase life-threatening flooding and mudslides, especially in steep terrain. That phrase is operational language for a landscape where rain does not simply fall. It moves. Picture the coast south of Acapulco before the center arrives. The Pacific is a moisture engine. Air moves in from the water, rises against the coastal mountains, cools, condenses, and releases rain. Streets in low towns fill first, then the gullies. Then the roads cut into the hillsides. Bridges begin receiving water from places that were dry a few hours earlier. A weak tropical cyclone can become deadly, not because its winds tear roofs away, but because its rain finds every slope. This is where the phrase El Niño protection begins to break down. NOAA's Atlantic. Oceanographic and Meteorological Laboratory explained the seasonal logic clearly in early June. El Niño generally reduces Atlantic hurricane activity by increasing vertical wind shear across the basin. Wind shear means the winds near the surface and the winds higher in the atmosphere are moving at different speeds or in different directions. A developing hurricane needs vertical alignment. It needs thunderstorms to stack over the center, release latent heat, lower pressure, and build a warm core. Strong shear tilts that structure apart. It disrupts the heat engine before it can organize. That is the protective mechanism. But it is not a wall. The same El Niño pattern that tends to suppress the Atlantic often makes the eastern and central Pacific more favorable. Warmer Pacific waters provide more energy, and the atmospheric circulation can become less hostile for storm formation in that basin. So the public hears one phrase: El Niño weakens hurricanes and turns it into a global rule. The atmosphere does not work that way. It moves risk, changes timing, changes odds, and does not erase tropical cyclones from the planet. The Climate Prediction Center placed the larger background into numbers on May 14th. And so neutral conditions were still present. But El Niño was likely to emerge soon, with an 82% chance during May through July and a 96% chance of continuing through the northern hemisphere winter. The same discussion warned that peak strength remained uncertain. The signal was strong enough to affect seasonal forecasting, but not precise enough to tell any coastline it had been spared. That is the important distinction. A seasonal outlook is not a shield. It is a probability map stretched across months. A 72-hour tropical forecast is something else entirely. It is an evaluation of a living system using satellite data, scatterometer passes, surface observations, model guidance, and forecasters watching the core evolve in real time. At the center of Tropical Depression 2E, the structure was still imperfect. An ASCAT overpass showed an east-west elongation of the low-level center. Convective banding was limited. The system was embedded on the eastern side of a broad, low-level gyre, west of a subtropical ridge. The water beneath it was very warm, greater than 30 degrees Celsius, and the air mass was moist. But the system lacked a well-defined inner core, and without that inner core, rapid intensification was not the favored outcome before landfall. Hold that thought, because it becomes important later. The ingredients for a major hurricane were not all present here at the same time. Warm ocean water was present. Moist air was present. But time over water was limited. The center was already close to the Mexican coast. Moderate easterly shear was being diagnosed. Land was approaching. The official forecast therefore stopped well below hurricane strength. So, the real failure is not El Niño protection collapsing against a Category 4 Atlantic storm. The real failure is treating basin-wide climate patterns as guarantees. El Niño can reduce Atlantic activity and still allow dangerous rainfall in Mexico. It can suppress one corridor and energize another. It can lower seasonal odds and still leave room for one damaging cyclone. The ocean did not contradict science. It contradicted the simplification of science. And this is where all begins, because the Atlantic silence on June 7 is not the end of the story. It is the baseline. To understand what protection means, we have to look at the invisible force that El Niño is supposed to create above the Atlantic: wind shear. The wind that tears storms apart. Over the Atlantic in early June, the most important weather feature is often the one no camera can see. It does not have an eye, it does not have spiral bands, it does not produce a visible wall of surf. It moves several miles above the ocean, above the trade winds, above the low clouds, in the layer where a developing cyclone either becomes vertically aligned or begins to lean apart. That feature is vertical wind shear. The phrase sounds technical, but the image is simple. Near the surface, air may be flowing from the east, feeding moisture into a weak tropical disturbance. Several miles above it, another current may be moving from the west, faster and drier. If those two layers are moving in different directions, or at sharply different speeds, the storm cannot stack itself. The thunderstorms that should rise over the center are pushed away. The heat release that should lower the pressure is displaced. The circulation near the ocean remains exposed, while the strongest cloud tops are carried downstream. A hurricane is not just a rotating storm. It is a vertical machine. It needs the lower atmosphere, the middle atmosphere, and the upper atmosphere to cooperate. Surface air flows inward and rises. Water vapor condenses into towering thunderstorms. Heat is released inside the core. Air exits near the top of the storm and spreads outward. If that column stays upright, the pressure falls and the winds increase. If it is tilted, the machine loses efficiency. This is why El Niño matters. During an El Niño pattern, warm water expands eastward across the equatorial Pacific. The trade winds weaken. Thunderstorm activity shifts. The Walker circulation changes position. Those shifts ripple outward into the tropical Atlantic. One of the most important consequences is stronger upper-level westerly wind across the Caribbean and tropical Atlantic. The National Weather Service describes the effect directly. El Niño increases vertical wind shear over the Atlantic, often shearing the tops from developing storms before a healthy circulation can form. That is the protective mechanism people are referring to when they say El Niño can weaken an Atlantic hurricane season. It does not cool every ocean. It does not drain heat from the Gulf. It does not make tropical waves disappear as they leave Africa. It changes the atmosphere above them. The distinction matters because the Atlantic hurricane season is not controlled by a single switch. A storm requires several ingredients at once: warm sea surface temperatures, a moist mid-level atmosphere, pre-existing spin, low enough pressure, weak enough shear, and enough time over water. El Niño mainly attacks one of those ingredients. It increases shear. When that shear is strong and placed over the right region, it can stop systems that would otherwise intensify. When it is weak, displaced, delayed, or interrupted, the protection becomes uneven. On May 14, 2026, the Climate Prediction Center issued an El Niño watch. The system was still officially ENSO neutral, with near-average sea surface temperatures in the east-central equatorial Pacific. But the forecast had changed. El Niño was likely to emerge soon, with an 82% chance during May through July, and a 96% chance of continuing through the Northern Hemisphere winter. The same discussion added an important caution. The peak strength remained uncertain, and no strength category exceeded a 37% chance. That caution is the part that rarely travels with the headline. A developing El Niño is not the same thing as a fully coupled, mature El Niño. In a mature event, the ocean and atmosphere reinforce each other. The warm pool in the central and eastern Pacific helps shift convection. The shifted convection changes the winds. The changed winds maintain the warm pool. The signal becomes coherent. But during the early stage, the atmosphere can lag behind the ocean. The Pacific can be warming while the Atlantic has not yet received the full shear response. In other words, the shield may be forming, but not everywhere, and not all at once. On June 7, the National Hurricane Center's Atlantic outlook showed exactly what a calm surface picture looks like. For the North Atlantic, the Caribbean Sea, and the Gulf of America, tropical cyclone formation was not expected during the next 7 days. There were no listed disturbances in the Atlantic basin. That does not mean the atmosphere was inactive. It means the Atlantic at that moment did not have a disturbance that forecasters expected to become a tropical cyclone. The Eastern Pacific did. The National Hurricane Center was issuing advisories on Tropical Depression Amanda, far from land, and newly formed Tropical Depression 2E near the southern coast of Mexico. It was also monitoring another broad low-pressure area offshore of Central America, with an 80% formation chance through 48 hours and 7 days. The basin contrast is the point. The Atlantic side was quiet. The Pacific side was organizing. Tropical depression. 2E showed why wind shear is only one part of the tropical cyclone problem. Its center was elongated. Its convective banding was limited. The National Hurricane Center noted moderate easterly shear in the area, although satellite cirrus motions did not strongly suggest significant shear. The storm was over sea surface temperatures greater than 30 degrees Celsius and embedded in a moist air mass, but it lacked a well-defined inner core, making rapid intensification unlikely before landfall. That sentence is a complete tropical diagnosis. Warm water alone was not enough. Moist air alone was not enough. Low pressure alone was not enough. The storm needed structure, alignment, and time. Without a compact core, a cyclone can sit over very warm water and still fail to become a major hurricane before land interaction disrupts it. But failure to become a major hurricane does not mean failure to become dangerous. The public advisory for 2E warned of 3 to 10 inches of rain, with isolated totals up to 12 inches across coastal Guerrero and Oaxaca. Tropical storm conditions were expected along the coast, but the rainfall hazard was more severe than the wind category suggested. Life-threatening flooding and mudslides were possible, especially in steep terrain. This is the second weakness in the idea of protection. Wind shear can reduce hurricane intensity and still leave a coastline facing a destructive tropical rain event. A sheared storm can have its strongest thunderstorms displaced from the center. If those thunderstorms are pushed over land, the damage pattern changes. The wind may underperform, while the rainfall overperforms. That detail matters in Mexico, Central America, the Caribbean, and the Gulf Coast. Mountains turn tropical rain into rapid runoff. Urban drainage systems fail before wind damage begins. Small rivers rise at night. Hillsides loosen. A tropical depression can kill without ever becoming a hurricane. The atmosphere does not protect people according to categories. Categories measure wind. They do not measure mudslides. They do not measure nighttime flash flooding. They do not measure how saturated the soil was before the storm arrived. So, when El Niño is described as protection, the word has to be narrowed. It is protection against some Atlantic hurricanes under some atmospheric arrangements. It is not protection against Pacific cyclones. It is not a protection against rainfall. It is not protection against a single storm finding a temporary gap in the shear, and it is not protection before the ocean-atmosphere system fully couples. That is why the early season pattern deserves attention. The Atlantic can remain empty while the Pacific becomes active. A storm can remain below hurricane strength while still producing dangerous rain. A seasonal forecast can be correct in broad terms and still miss the human-scale disaster hidden inside a weak cyclone. The question is not whether El Niño matters. It does. The question is where the shear is, when it arrives, how strong it becomes, and whether any disturbance can be organized before the protection locks into place. The ocean heat that refuses to leave. Before a storm has a name, before a warning map is colored, before coastal police begin moving barricades toward the seawall, the ocean has already made its first decision. It has either stored enough heat to feed the atmosphere above it, or it has not. The satellite can show clouds, the buoy can show pressure, the radar can show rain moving toward land. But beneath all of that, below the broken surface of the water, the real fuel supply is measured quietly in temperature, depth, and time. A tropical cyclone begins with a disturbance, but a disturbance is only the seed. NOAA's ocean guidance describes one of the basic thresholds clearly. Hurricanes require warm ocean water, generally at least 80 degrees Fahrenheit or 27 degrees Celsius at the surface. NOAA's National Ocean Service gives the more technical version. Water at least 26.5 degrees Celsius over a depth of 50 meters can power a hurricane. But even when the ingredients are present, development is not guaranteed. That last part is important. The ocean can load the system, but the atmosphere still has to permit the trigger. Along the southern coast of Mexico, on June 7, 2026, the Pacific had already crossed that threshold. The National Hurricane Center discussion for tropical depression, 2E, noted sea surface temperatures greater than 30 degrees Celsius near the system. That is not marginal water. That is water warm enough to supply deep convection, feed thunderstorm towers, and maintain heavy rain bands if the low-level center remains close enough to the moisture plume. The storm itself did not look like a classic major hurricane. It had no clean eye. Its circulation was still somewhat broad. The cloud shield spread unevenly. The center was close to land, moving slowly, with only a short period left over open water. But beneath it, the ocean was not weak. That detail matters because public attention often waits for wind speed. The ocean does not. Warm water works by evaporation. Moist air rises from the surface. Inside thunderstorm towers, water vapor condenses into droplets and ice particles, releasing latent heat. That heat lowers pressure in the core, encourages more air to flow inward, and allows the circulation to tighten. The storm becomes a heat engine, converting ocean warmth into wind, rain, and pressure falls. When the surrounding winds are light and the inner core is organized, the machine becomes efficient. When shear is present or land is nearby, the machine loses efficiency, but it does not necessarily shut down. This is the uncomfortable part of the El Niño shield. El Niño can make the Atlantic atmosphere more hostile by increasing vertical wind shear, and NOAA's Atlantic Oceanographic and Meteorological Laboratory identifies that shear as the main reason El Niño usually reduces Atlantic hurricane activity. But the same NOAA explanation also notes the other side of the pattern. El Niño often increases activity in the eastern and central Pacific, where warmer waters and more favorable atmospheric conditions can support storm development. So, the shield is regional. It does not cover every basin. It does not remove heat from the eastern Pacific. It does not stop all tropical rain events. And it does not mean every warm ocean will remain harmless. On the Atlantic side, the official map was still empty. The National Hurricane Center's outlook for the North Atlantic, Caribbean Sea, and Gulf of America stated that tropical cyclone formation was not expected during the next 7 days. That is a meaningful forecast. It means there was no Atlantic disturbance that forecasters expected to organize during that period. It also means there was no official basis for a Category 4 Atlantic hurricane forming within 72 hours. But the Eastern Pacific outlook was not empty. The same operational cycle listed tropical depression, Amanda, tropical depression 2E near southern Mexico, and a separate broad low-pressure area offshore of Central America. That Central American disturbance carried an 80% chance of formation through 48 hours and 7 days, and forecasters warned that heavy rainfall and life-threatening flash flooding were possible across parts of Costa Rica, Nicaragua, El Salvador, and Guatemala, regardless of whether formal development occurred. There is a pattern inside that language. The atmosphere may not care whether the public gets a named storm. The rain hazard can arrive first. The flooding can begin before the category exists. The mudslides can happen while the circulation is still technically disorganized. Ocean heat becomes especially dangerous when it extends downward. A thin layer of warm surface water can be cooled quickly by a storm's own winds. As the cyclone churns the sea, colder water rises from below. That process can weaken the storm by cutting off its energy supply. But when the warm layer is deep, the storm mixes warm water upward instead of cold water. The engine keeps feeding. That is why forecasters look not only at sea surface temperature but at ocean heat content and the depth of the warm layer. In a coastal setting, time becomes the limiting factor. Tropical depression. 2E did not have days to sit over warm Pacific water. Its center was already near the coast, and land interaction was expected to weaken it. That prevented the kind of dramatic strengthening implied by a major hurricane headline. But the same slow movement near warm water also supported a different danger. Persistent rain moving into steep terrain. The mountains behind the Mexican Pacific coast change the behavior of a tropical cyclone. Moist air coming in from the ocean is forced upward. As it climbs, it cools. As it cools, water vapor condenses. Rainfall increases along the slopes. A modest tropical depression over flat land can be a nuisance. The same depression against a coastal mountain range can become a flood event. Roads become channels. Ravines become rivers. Hillsides begin to fail from below. This is why wind categories can mislead. The Saffir-Simpson scale is a wind scale. Category 4 begins at 130 miles per hour and describes the potential wind damage. It does not classify rainfall, storm surge, landslides, or freshwater flooding. A storm below hurricane strength can still produce lethal water impacts, and a major hurricane's category does not fully describe what it will do after landfall. The bigger question is why the ocean remains so ready even when the atmosphere is supposed to be hostile. The answer is that climate signals do not cancel each other cleanly. El Niño changes circulation. Seasonal outlooks change probability. Local water temperature changes energy availability. Storm structure changes efficiency. Topography changes rainfall impact. A single coastline experiences the overlap, not the headline. NOAA's 2026 outlook, summarized by AOML, gave the Atlantic a 55% probability of a below-average season, with 8 to 14 named storms, 3 to 6 hurricanes, and 1 to 3 major hurricanes. That forecast was not a promise of calm. It was a basin-scale probability built from climate models, historical analogs, and expected El Niño influence. NOAA's own explanation emphasizes that seasonal outlooks are probability-based predictions of overall activity, not specific forecasts for individual storms. That distinction becomes critical when the ocean heat refuses to leave. A below-average Atlantic season can still produce a damaging landfall. A quiet Atlantic week can coincide with an active Eastern Pacific. A tropical depression can fail to become a hurricane and still deliver catastrophic water. The ocean does not announce danger in categories first. It stores it. It holds it below the waves, waiting for low pressure, moisture, weak enough shear, and enough time. When those ingredients align, the atmosphere begins taking heat from the sea and turning it into motion. Sometimes the result is a Category 4. Sometimes it is 12 inches of rain on a mountainside. The number on the map is only the final translation. The fuel was there earlier. The Pacific Basin that El Niño awakens. Along the Pacific coast of Central America, the first sign is often not wind. It is the thickness of the air before sunrise. Fishing boats sit in harbors under low gray clouds. The surf arrives in slow, uneven lines. Farther inland, the mountains disappear behind curtains of rain long before any formal storm center reaches land. The sky does not need an eye to become dangerous. It only needs moisture, lift, and time. That is why the Eastern Pacific behaves differently under El Niño. While the Atlantic is watched for the storms that threaten Florida, the Caribbean, and the Gulf Coast, the Pacific side of Mexico and Central America often becomes the basin where the atmosphere quietly opens a door. NOAA's Atlantic, Oceanographic and Meteorological Laboratory, states the contrast directly. El Niño generally reduces Atlantic hurricane activity by increasing vertical wind shear, but it often increases activity in the eastern and central Pacific, where warmer waters provide more energy and conditions can become more favorable for storm formation. The geography of that basin matters. The eastern Pacific hurricane zone is a narrow corridor of warm water running west of Central America and southern Mexico. Tropical waves can move out of the Caribbean and Central America, cross the mountains, and redevelop over the Pacific. Monsoon trough circulations can gather moisture close to the coast. Low-pressure areas can form just offshore, close enough to land that they do not need a long track to become hazardous. On June 7, 2026, the Atlantic outlook remained silent. The National Hurricane Center said tropical cyclone formation was not expected in the North Atlantic, Caribbean Sea, or Gulf of America during the next 7 days. In public terms, that sounded reassuring. In meteorological terms, it was only half the map. The Eastern Pacific outlook on the same operational page was not empty. The National Hurricane Center was issuing advisories on Tropical Depression Amanda, well east-southeast of the Hawaiian Islands, and on newly formed Tropical Depression 2E near the southern coast of Mexico. It was also tracking a broad area of low pressure offshore of Central America, labeled EP92, with an 80% chance of formation through 48 hours and through 7 days. That detail is the hinge. The Atlantic had no expected development. The Eastern Pacific had 2 active tropical depressions and a third likely formation zone. The public phrase El Niño protection was therefore correct only if the word Atlantic stayed attached to it. Remove that word, and the meaning changes completely. The Pacific disturbance near Central America was not a remote ocean feature. It was moving slowly northward toward the coast. The National Hurricane Center warned interests along the Pacific coasts of northwestern Costa Rica, Nicaragua, Honduras, and El Salvador to monitor it. Regardless of whether it became a tropical cyclone, heavy rainfall and life-threatening flash flooding were possible across portions of Costa Rica, Nicaragua, El Salvador, and Guatemala through early in the week. The phrase, regardless of development, is one of the most important phrases in tropical forecasting. It means the atmosphere already contains enough moisture and organization to create damage, even if the system never receives a name. A tropical depression has legal and operational meaning. A named storm has media meaning. But a flood does not wait for either one. It follows terrain. Central America is built for rain to become violent. The coastal plain can be narrow. Volcanoes and mountains rise steeply behind the shoreline. Roads often cut through slopes that have been shaped by older landslides. Rivers descend quickly from high terrain to populated valleys. When tropical moisture arrives from the Pacific and is forced upward against that landscape, rainfall totals can multiply in a way that flat maps do not show. This is the side of El Niño that is easy to misunderstand. The warming begins in the equatorial Pacific, where sea surface temperatures become above average and trade winds weaken. The Climate Prediction Center reported on May 14 that ENSO-neutral conditions still existed, but an El Niño watch was in effect, with an 82% chance of El Niño emerging during May through July, and a 96% chance of continuing through the Northern Hemisphere winter. The same discussion noted above-average subsurface temperatures across the equatorial Pacific, and said the ocean atmosphere system had not yet fully coupled into a mature event. That incomplete coupling matters. During the transition period, the atmosphere can behave unevenly. The Pacific can already show warmer subsurface and surface signals while the broader circulation is still organizing. The Atlantic may begin leaning toward suppression, while the Pacific begins leaning toward activity. The result is not a clean global shutdown of hurricanes. It is a redistribution of risk. A fully developed tropical cyclone needs low shear, high moisture, warm water, and a disturbance with enough spin. In the eastern Pacific, El Niño often helps by warming the ocean and altering the upper-level wind pattern in a way that allows storms to organize. In the Atlantic, the same climate state often hurts storms by increasing shear. One basin receives interference, another receives permission. That is the mechanical contradiction behind the word protection. On satellite, the contradiction would not look philosophical. It would look like clouds. Over the Atlantic, clean blue gaps. Over the eastern Pacific, clusters of deep convection pulsing near low-pressure centers. Near the coast of Mexico, rain bands drawn into Tropical Depression 2E. Farther southeast, a broad gyre offshore of Central America, turning slowly under very moist air. Westward, Amanda weakening or drifting over open water, still present as part of the basin's early season activity. The significance was not the strength of one storm. It was the spacing. Multiple features were active across the same basin while the Atlantic remained quiet. That pattern is exactly what seasonal climate logic would allow under El Niño. The danger is that public attention often follows the wrong ocean. For Mexico and Central America, the eastern Pacific is not distant. It is the weather-facing wall. Storms that form there can parallel the coast, brush the mountains with rain, stall near land, or move inland quickly. Some become hurricanes, some never do, but the rainfall corridor can remain active for days as moisture keeps feeding into the same terrain. This is why a Category 4 headline can distort the real threat. A major hurricane would be visually dramatic, easy to map, easy to rank. But the immediate verified hazard was different. Early eastern Pacific activity, warm water, a developing El Niño background, and tropical rainfall threats close to vulnerable terrain. The official forecast did not support an Atlantic Category 4 within 72 hours. The official forecast did support something less cinematic and more practical. The Pacific side was already awake. The atmosphere had not broken the rules. It had followed the part of the rules that receives less attention. El Niño can shield the Atlantic and expose the Pacific at the same time. It can lower one basin's odds while raising another's. It can reduce the number of hurricanes people expect to track across the Atlantic and still produce dangerous storms where the ocean, mountains, and moisture are aligned. The next warning, then, is not only about wind speed. It is about location. It is about which basin is being watched, which coast is being ignored, and which kind of danger is being measured. Because the eastern Pacific does not need to create a Category 4 hurricane to prove that the season has begun. It only needs to send rain into the mountains. The storm that did not need a category. The southern coast of Mexico does not need a perfect hurricane to become dangerous. A storm can arrive unfinished. Its center can be broad. Its winds can remain below hurricane strength. Its cloud shield can look uneven on satellite, with the strongest thunderstorms displaced from the middle. On an ordinary map, that kind of system appears weak. On a mountain slope above Guerrero or Oaxaca, it can become something else entirely. The official language from the National Hurricane Center made that distinction plain. Tropical depression. 2E was not a hurricane. At 3 o'clock in the afternoon Central Standard Time on June 7, 2026, its maximum sustained winds were near 35 miles per hour, with higher gusts. Some strengthening was forecast, and the depression was expected to become a tropical storm before reaching the coast, but the forecast did not point toward a major hurricane. The center was located near 15.7 degrees north and 99.7 degrees west, moving slowly toward the northeast at about 3 miles per hour. That slow motion was the detail to watch. A fast-moving weak storm can pass through before the rainfall maximum has time to accumulate. A slow-moving weak storm can keep drawing moisture inland hour after hour, feeding rain over the same hills, the same river basins, and the same road cuts. The wind number stays small, the water number grows. The warning area ran from Laguna de Chacahua to Tecpan de Galeana, a stretch of the Mexican Pacific coast that includes beaches, low towns, steep terrain just inland, and road networks climbing toward the interior. Tropical storm conditions were expected somewhere inside that warning area within 24 hours. But the rainfall forecast was sharper, 4 to 10 inches, with isolated maximum totals up to 12 inches across coastal portions of Guerrero and Oaxaca through Monday night. That rainfall, forecasters wrote, could produce life-threatening flooding and mudslides, especially in steep terrain. The words "especially in steep terrain" carry more information than they appeared to at first. Rainfall on flat land spreads outward. Rainfall on steep land accelerates downward. It enters ravines, culverts, and narrow river channels. It gathers soil, branches, stones, and loose construction material. A flood in this terrain is not only rising water, it is moving debris. This is why a tropical depression can be more dangerous than its category suggests. The Saffir-Simpson hurricane wind scale begins with Category 1 at 74 miles per hour and reaches Category 4 at 130 miles per hour. It is a wind scale. The National Hurricane Center states that it does not account for other hurricane-related hazards such as storm surge, rainfall flooding, and tornadoes. That limitation is not a footnote. It is the reason weak systems continue to kill. 2E's internal structure supported the lower wind forecast. In the forecast discussion, the National Hurricane Center described little change in overall organization. An ASCAT overpass showed an east-west elongation of the low-level center. Convective banding features were limited. A couple of heavy shower and thunderstorm bands were bringing significant rainfall to portions of southern Mexico, but the storm had not built the compact, symmetrical core associated with rapid intensification. That detail matters. A cyclone that lacks a tight core cannot efficiently convert ocean heat into wind. The pressure gradient stays broader. The strongest thunderstorms may flare and collapse without wrapping cleanly around the center. The system can remain below hurricane strength even over very warm water, but rainfall does not require the same inner core precision that wind intensification does. A disorganized tropical cyclone can still act as a conveyor belt for moisture. The coast magnifies that conveyor belt. Warm Pacific air flows inland and is forced upward by terrain. As the air rises, it cools. As it cools, water vapor condenses into clouds and rain. This process, called orographic lift, can take a tropical rain band that looks manageable offshore and make it heavier once it reaches the mountains. The center of the storm does not need to make landfall directly over a town for that town to flood. The rain shield only needs to connect with the slope. On satellite imagery, the most dangerous part of a weak tropical cyclone is often not visually elegant. It may not have the clean spiral that viewers associate with hurricanes. It may be a ragged mass of cold cloud tops pulsing in bursts, with dry slots and exposed low clouds around it. To a casual observer, that looks less threatening. To a hydrologist, it can be enough. Central America faced a related problem at the same time. Offshore of Central America, a broad area of low pressure called EP92 was producing showers and thunderstorms. The National Hurricane Center gave it an 80% chance of tropical cyclone formation through 48 hours and through 7 days. The outlook said environmental conditions were conducive for further development, and that a tropical depression was likely to form during the next day or two while the system moved slowly northward toward the coast. Regardless of development, heavy rainfall and life-threatening flash flooding were possible across portions of Costa Rica, Nicaragua, El Salvador, and Guatemala. There is a pattern in those words. The danger was being described before classification. Interests were told to monitor the system before it had a name. Flooding was possible regardless of development. That is the operational reality of tropical meteorology in mountainous coastal regions. The category arrives late. The rain can arrive early. The question is not whether Tropical Depression 2E was powerful. By wind, it was not. The question is whether it had the correct ingredients to create a water emergency. It had very warm water nearby. It had a slow forward motion. It had heavy shower bands already reaching the coast. It had steep terrain in the rainfall zone. It had an official forecast of up to 12 inches in isolated areas. The category did not capture that combination. A hurricane headline can be wrong, and the hazard can still be real. There was no verified Atlantic Category 4 forming within 72 hours. There was, however, a verified tropical depression near southern Mexico, an active warning area, a serious rainfall forecast, and another likely development zone offshore of Central America. The atmosphere was not producing the storm people were being told to fear. It was producing the kind of storm people often underestimate. By the time the wind number becomes impressive, some disasters have already begun. The rivers have already responded. The slopes have already weakened. The roads have already started to disappear under brown water. Tropical danger does not always arrive with an eye. Sometimes it arrives as a rain band that refuses to move. The forecast cone people misread. A storm map looks simple until it becomes personal. One white shape curves across the ocean. A black line runs through its center. Small dots mark future positions, each one placed 12 or 24 hours farther into the forecast. On television, the image appears for a few seconds. Online, it is cropped, reposted, enlarged, and stripped of the explanation written beneath it. Within minutes, people begin doing what people always do with maps. They search for their town. If the town is inside the cone, they worry. If the town is outside it, they breathe easier. That reaction is understandable. It is also the beginning of the problem. The National Hurricane Center's forecast cone does not show the full area that will experience storm impacts. It represents the probable track of the center of a tropical cyclone. The cone is built by enclosing circles around forecast points at 12, 24, 36, 48, 60, 72, 96, and 120 hours. Each circle is sized so that 2/3 of historical official forecast errors from the previous 5 years fall inside it. In plain terms, the center of the storm is expected to remain inside the cone about 2/3 of the time, while about 1/3 of historical cases fall outside it. That definition changes the entire image. The cone is not a shield line. It is not an impact boundary. It is not the edge of the storm. It is a statistical track corridor for the center only. A town outside the cone may still receive storm surge, destructive surf, flooding rainfall, landslides, or tropical storm force winds. A town inside the cone may receive only outer rain bands. The graphic is useful, but only if it is read as a forecast of position, not a forecast of consequences. For 2026, the National Hurricane Center lists the Atlantic 72-hour cone radius at 95 nautical miles. In the eastern and central North Pacific, the 72-hour radius is 78 nautical miles. By 120 hours, the Atlantic radius expands to 200 nautical miles, while the eastern and central Pacific radius is 138 nautical miles. Those numbers are not chosen because one storm looks more uncertain than another. They come from official forecast error statistics from 2021 through 2025. A viewer looking at a cone often assumes its width reflects the size of the storm. it does not. A small tropical storm and a large hurricane can use the same statistical cone structure if their forecast periods are the same. The cone grows with time because track errors usually grow with time. It does not expand because the cyclone is physically spreading outward. The storm's actual wind field, rain shield, and surge zone have to be read from other products. That is where the misunderstanding becomes dangerous. A tropical cyclone is not a point. The center is only the coordinate around which the rest of the system is organized. Rain bands can extend hundreds of miles away. Tropical storm force winds may spread unevenly, wider on one side than the other, depending on forward speed, pressure gradient, and interaction with land. The heaviest rainfall can fall far from the center if wind shear displaces convection. Storm surge can occur in places that never see the center pass overhead. The cone answers one question: where might the center go? It does not answer the larger question: where will the damage be? Along the Pacific coast of Mexico, this distinction matters immediately. Tropical depression. 2E did not require a major hurricane forecast to create a hazard. Its center was close to the coast, its forward motion was slow, and its rain bands were already affecting southern Mexico. The official wind forecast stayed far below Category 4 strength, but the rainfall forecast included 4 to 10 inches, with isolated totals up to 12 inches across coastal Guerrero and Oaxaca. The warning language pointed toward flooding and mudslides, not catastrophic wind. The cone could show track uncertainty. It could not show every ravine where water might accelerate downhill. The human eye is drawn to the line in the middle. That line is the forecast track, and it is usually the most visually dominant element on a simplified map. But the center line is not a promise. It is the current best forecast, surrounded by a probability envelope. Forecast models adjust with each new advisory. Aircraft data, satellite estimates, scatterometer passes, radar fixes, and surface observations can all shift the center location. A small adjustment offshore can become a large difference for a coastline, especially when the storm is moving almost parallel to land. The Pacific systems near Mexico and Central America show another weakness of cone-centered thinking. EP 92, the broad area of low pressure offshore of Central America, was not yet a named storm when forecasters warned of heavy rainfall and life-threatening flash flooding. Without a classified cyclone, there is no familiar cone for many viewers to fixate on. Yet the hazard existed. Moisture was gathering. Environmental conditions were favorable. The system was expected to move slowly toward the coast. Rainfall risk did not wait for the graphic. Forecast communication has to solve a difficult problem. The public needs a clean image quickly. Emergency managers need precise hazard information. Meteorologists need to describe uncertainty without making people feel that nothing is known. The cone became powerful because it does one job well. It visualizes track uncertainty in a form people can understand. Its weakness is that people often ask it to do jobs it was never designed to do. The better reading starts outside the cone. Look for watches and warnings along the coast. Look for rainfall totals. Look for storm surge products when available. Look for wind speed probability maps, local National Weather Service statements, and discussions that explain asymmetry, shear, terrain, and timing. The cone is the skeleton. The impacts are the body around it. In an El Niño season, this becomes even more important. Stronger Atlantic shear can keep storms tilted, ragged, or displaced. A sheared storm may place its heaviest rain far from the center, which means the center track can become less representative of the real hazard footprint. A weak cyclone near mountains may be more dangerous on its wet side than on its windy side. The public map may look less alarming precisely when the hydrological risk is increasing. The atmosphere is not misleading anyone. The graphic is not wrong. The error is in the reading. A forecast cone is a carefully built statistical product based on years of official track errors and updated each season as forecast skill changes. It is evidence, not certainty. It is guidance, not geography. It shows where the center may travel, not where the storm will be felt. A coastline does not flood according to the center line. A hillside does not fail because it was inside a white shape. A river does not check whether the storm had a name. The water responds to rainfall, slope, soil, drainage, and duration. Those variables live outside the cleanest part of the map. The rainfall map that matters more. The most important map in a weak tropical storm is often the least dramatic one. It does not show a black track line cutting through the ocean. It does not use a category label. It does not invite the eye toward a single center. Instead, it spreads color unevenly across land, coast, mountain, and river basins, showing where water is expected to fall after the wind has finished getting most of the attention. That map is the rainfall forecast. In operational meteorology, the technical term is Quantitative Precipitation Forecast, or QPF. It describes the amount of liquid precipitation expected to fall over a defined period of time. The National Weather Service definition is precise. Precipitation amount is the expected quantity of liquid precipitation accumulated over a 6-hour period, and QPF includes liquid equivalent precipitation when snow or ice is involved. The Weather Prediction Center has been issuing these forecasts and their predecessor versions since 1960. The plain language translation is simpler. A QPF map asks how much water is coming down, where it will land, and how long the atmosphere will keep delivering it. A tropical cyclone track forecast begins with motion. A rainfall forecast begins with accumulation. The forecaster has to look at the storm's moisture field, forward speed, convective bursts, steering currents, terrain, and the possibility of rain bands training repeatedly across the same area. A track line may shift 20 miles and still tell a broadly similar story. A rainfall maximum shifting 20 miles can move the flood threat from one watershed to another. Near southern Mexico, that difference was not theoretical. Tropical depression. 2E was close to the coast, moving slowly northeast, and expected to produce heavy rain across coastal Guerrero and Oaxaca. The National Hurricane Center forecast 4 to 10 inches of rainfall, with isolated maximum totals near 12 inches, and warned that life-threatening flooding and mudslides were possible, especially in steep terrain. The wind forecast stayed modest. The rainfall forecast carried the sharper danger. A road on a coastal slope does not respond to sustained wind speed first. It responds to water entering the soil. At the beginning of a rain event, some of that water infiltrates the ground. Small channels collect runoff. Leaves, loose stones, and sediment begin moving downhill. If the rain continues, the soil loses its ability to absorb more. Water that once disappeared into the ground begins running over it. The slope becomes heavier, less stable, and more likely to fail. That is why mountains change tropical forecasting. Warm Pacific air arrives from the ocean carrying moisture. When it meets rising terrain, the air is forced upward. Rising air expands and cools. Cooler air holds less water vapor. Condensation increases, cloud depth grows, and rainfall intensifies along the windward slopes. This orographic process can make the wet side of a storm more dangerous than the circulation center itself. The official maps have to compress that complexity into colors. A broad, light green field may show 1 to 2 inches. Yellow and orange may indicate heavier totals. Red, purple, or white areas often mark the places where rain becomes exceptional. But the map is not simply a picture of clouds. It is a judgment built from model guidance, satellite observations, surface reports, radar where available, and forecaster experience with terrain. The Weather Prediction Center's QPF products are used by river forecast centers and local forecast offices to support river and flash flood warning operations. That operational chain matters. Rainfall forecasts do not end at the map. They flow into hydrologic models. Those models estimate how rivers, streams, and soils will respond. Emergency managers look at roads, drainage systems, bridges, shelters, and evacuation routes. A rainfall maximum over open countryside has one set of consequences. The same maximum over a steep populated basin has another. In Central America, the problem was wider than one depression. The National Hurricane Center was also monitoring a broad, low-pressure area offshore of Central America, designated EP92, with an 80% chance of formation within 48 hours and 7 days. The outlook warned that, regardless of whether the system developed into a tropical cyclone, heavy rainfall and life-threatening flash flooding were possible across portions of Costa Rica, Nicaragua, El Salvador, and Guatemala through early in the week. The phrase, regardless of development, belongs at the center of the rainfall story. It removes the false comfort of classification. A system can remain a disturbance and still deliver enough moisture to flood rivers. It can fail to earn a name and still block roads. It can never reach hurricane strength and still produce a disaster after nightfall in a valley where water rises faster than people can see it. Categories cannot describe that. The Saffir-Simpson Hurricane Wind Scale measures sustained wind. It does not account for rainfall flooding, storm surge, tornadoes, or other hazards. A Category 4 label says something important about potential wind damage, but it says almost nothing about how 12 inches of rain will behave on unstable terrain. A tropical depression label says the wind is weak, but not that the water is harmless. In flood disasters, depth is only part of the danger. Speed matters, mud matters, night matters. A few inches of fast-moving water can sweep vehicles from low crossings. Debris can block culverts, forcing water onto roads that were passable minutes earlier. Saturated slopes can release without warning. In a mountainous tropical setting, a flood is not only a river rising in place. It is the landscape reorganizing itself under gravity. That is why the rainfall map deserves more attention than the center line. The center line shows where a circulation might travel. The rainfall map shows where the atmosphere may keep delivering water. One is about location. The other is about consequence. When a storm is weak, sheared, slow, or interacting with terrain, consequence can separate sharply from the center. The lesson from the Eastern Pacific setup was not that a catastrophic major hurricane was secretly imminent. The Atlantic Outlook still stated that tropical cyclone formation was not expected during the next 7 days. The verified danger was more specific and more immediate. Active Pacific systems, warm water, slow-moving disturbances, and heavy rainfall directed toward mountains and coastal communities. A rainfall map asks viewers to think less like storm chasers and more like hydrologists. Where will the band stall? Which slopes face the inflow? Which river basins are already wet? Which roads cross low water? Which towns sit below steep drainage channels? Those questions do not fit neatly into a category number, but they are the questions that determine where the first emergency calls begin. The sky may look disorganized. The center may be weak. The wind may never become historic. But if the colors on the rainfall map deepen over the wrong terrain, the storm has already found its weapon. The mountains that turn rain into disaster. Between the Pacific Surf and the interior highlands, southern Mexico leaves very little room for water to move slowly. The coast is not a broad, forgiving shelf in every place. In many stretches, communities, roads, river mouths, and steep slopes sit close together. Rain arriving from the ocean does not spread gently across a flat plain. It climbs into terrain, gathers speed, and begins looking for the lowest path downhill. That is where a tropical cyclone's weakest-looking hazard can become its most dangerous one. The advisory attached to tropical depression, 2E, described a system with modest winds, a slow northeast motion, and a center still offshore from Acapulco. It placed a tropical storm warning from Laguna de Chacagua to Tecpan de Galeana, and forecast tropical storm conditions within 24 hours. But the more important line was not about the wind. Rainfall totals of 4 to 10 inches were expected across coastal Guerrero and Oaxaca, with maximum totals near 12 inches possible, and the National Hurricane Center warned that this could produce life-threatening flooding and mudslides, especially in steep terrain. Steep terrain changes the physics of rain. On level ground, water has time to pool, infiltrate, overflow, and expand outward. On a hillside, gravity begins sorting the landscape almost immediately. The first inch wets the soil. The second inch fills pore spaces. The next bands of rain begin running across the surface. Small channels that were dry in the morning become active by afternoon. Loose rock and soil begin to move. Drainage paths that look minor on a dry day become the only routes available for thousands of tons of water. A tropical storm does not have to be symmetric for that process to begin. It does not need a closed eye. It does not need category strength. The rain bands only have to keep arriving. The U.S. Geological Survey defines debris flows as fast-moving landslides that usually occur during intense rainfall or rapid snowmelt, and often begin on hillsides or mountains. The same agency notes that they can move at speeds reaching or exceeding 35 miles per hour, and can carry boulders, trees, and cars. If they enter steep stream channels, they can travel several miles into areas that may not recognize they are in danger. That last part is the hidden geography of a tropical rain disaster. The place where the slope fails may not be the place where the damage is counted. A scar opens high above a road. Mud enters a narrow channel. The channel accelerates it. By the time the flow reaches a bridge, a village edge, or a low crossing, it is no longer only mud. It is water, soil, trees, stones, metal, and whatever the mountain has released on the way down. Forecast language compresses all of that into one word: mudslides. The word is easy to pass over. It sounds smaller than hurricane. It sounds local, almost ordinary. But in tropical terrain, a mudslide is not a side effect. It is one of the main ways the storm enters the land. Wind acts through air. Flooding acts through channels. Debris flows act through mass. They transform rainfall into moving ground. Across Central America, the same setup was being watched offshore. The National Hurricane Center identified a broad, low-pressure area, called EP92, gave it an 80% chance of development through 48 hours and 7 days, and warned that heavy rainfall and life-threatening flash flooding were possible across portions of Costa Rica, Nicaragua, El Salvador, and Guatemala, regardless of whether the system formally developed. The phrase "regardless of development" is especially important in mountainous countries. It means the atmosphere is already capable of producing damage before the storm classification catches up. A system can still be labeled a low-pressure area, while its moisture plume is already pointed at volcanic slopes, river valleys, and communities built along drainage corridors. The cyclone label is administrative. The rainfall response is physical. Roads are often the first visible failure point. A mountain road is a negotiation between engineering and water. It crosses gullies, cuts through slopes, and depends on culverts staying open. During a tropical rain event, leaves and branches clog drainage channels. Sediment piles against bridge supports. Water crosses pavement where drivers expect asphalt. The National Weather Service warns that only 6 inches of fast-moving floodwater can knock over an adult. 12 inches of rushing water can carry away most cars, and 2 feet can carry away SUVs and trucks. In a coastal mountain setting, those thresholds can be reached quickly. The dangerous crossing may not be a large river. It may be a dip in a rural road, a concrete ford, a washed-out shoulder, or the entrance to a bridge where water has found a new channel. At night, the surface looks flat until headlights hit it. By then, the depth and speed are already difficult to judge. The soil itself has a timeline. Dry soil can absorb the opening stage of rainfall. Partly saturated soil accepts less. Fully saturated soil becomes heavy, weaker, and more likely to slide. If roots are shallow, if slopes have been cut for roads, if drainage is blocked, or if earlier rains have already raised water content, the threshold lowers. The storm does not need to deliver a historic total everywhere. It only needs to exceed the local slope's tolerance in one vulnerable place. This is why regional rainfall forecasts can hide village-scale danger. 4 inches over a wide area is one message. 12 inches on a steep basin is another. A national map may show a broad zone of risk, but the actual disaster may occur in a narrow drainage where rain, slope, soil, and settlement overlap. Wind categories cannot read that landscape. A Category 4. Hurricane can be catastrophic, but a tropical depression near steep terrain can still create lethal conditions through water and ground movement. The National Hurricane Center's warning for 2E did not depend on major hurricane strength. It depended on rainfall amount, slope, and timing. Those were enough. The atmosphere's role is to deliver moisture. The mountains decide what the moisture becomes. In one valley, it is runoff. In another, a river rises. Above a road, it may become a slope failure. Below a ravine, it may arrive as a debris flow with almost no warning. That is the part a satellite loop cannot fully show. From space, the cloud tops bloom and fade. On the ground, water enters the landscape one channel at a time until the landscape begins moving back. The false comfort of a quiet Atlantic. A blank tropical map has a particular effect on people. It looks final. The ocean is shown in blue. The coastlines are clean, and the disturbance markers are absent. No orange circle, no red-shaded development zone, no cones, no advisory package scrolling beneath a storm name. For anyone watching from Florida, the Carolinas, the Gulf Coast, or the Caribbean, that kind of map can feel like an answer. On June 7, 2026, the National Hurricane Center gave the Atlantic that exact appearance. Its tropical weather outlook for the North Atlantic, Caribbean Sea, and Gulf of America stated that tropical cyclone formation was not expected during the next 7 days. In the language of operational forecasting, that was a clear short-range signal. No Atlantic system was being monitored for likely development. No Category 4 hurricane was forming there within 72 hours. The mistake begins when that sentence is asked to say more than it says. A 7-day outlook is not a seasonal verdict. It is not a coastal guarantee. It is not a statement about every tropical basin. The National Hurricane Center's own product descriptions explain that the graphical tropical weather outlook identifies areas of disturbed weather and assigns formation probabilities for tropical cyclones during the next 2 and 7 days. Gray indicates development is not expected. Yellow indicates low probability, orange medium probability, and red high probability. The colors describe formation potential within a forecast window, not the permanent state of the ocean. That distinction is where public understanding often breaks. A quiet Atlantic map is treated as protection. In reality, it is only a snapshot of one basin during one forecast period, using the evidence available at issuance time. It can be accurate and still incomplete. It can be reassuring and still leave danger nearby. The season itself had only just begun. The Atlantic hurricane season runs from June 1 through November 30. The Eastern Pacific season begins earlier, on May 15th, and also continues through November 30th. That calendar detail matters because the Pacific can become active before the Atlantic has even settled into its summer pattern. A quiet Atlantic in early June can coexist with a very different Pacific. That is exactly what the operational map showed. While the Atlantic outlook carried no expected development, the Eastern Pacific outlook listed active systems: Tropical Depression Amanda, Tropical Depression 2E near the southern coast of Mexico, and another area of disturbed weather offshore of Central America with high development odds. The contrast was not subtle. One basin was quiet. The neighboring basin was already producing alerts, rainfall threats, and tropical advisories. The word protection becomes fragile under that contrast. El Niño is often described as suppressing Atlantic hurricane activity, and that description is generally correct. By changing tropical Pacific temperatures and atmospheric circulation, El Niño tends to increase vertical wind shear over the Atlantic, making it harder for storms to stack vertically and intensify. But the same broad pattern can favor more activity in the eastern and central Pacific, where warmer waters and different upper-level winds can make tropical cyclone formation easier. Protection, then, is not a global condition. It is a redistribution of probability. The Climate Prediction Center's May 14 discussion placed the background state in cautious terms. ENSO-neutral conditions were still present, but El Niño was likely to emerge soon, with an 82% chance during May through July and a 96% chance of continuing into the Northern Hemisphere winter. The forecast did not describe an already mature, fully settled El Niño shield. It described a developing climate signal, still moving toward its stronger phase. That timing matters. The atmosphere does not obey the headline instantly. During transition periods, ocean temperatures, pressure patterns, upper-level winds, and tropical convection can align unevenly. One basin may begin showing the influence before another. The Atlantic may look suppressed for a week, while the Eastern Pacific is already responding to warmer water and favorable conditions. A viewer who only watches the Atlantic misses the side of the pattern where the energy has gone. Even inside the Atlantic, a quiet week does not remove the larger seasonal risk. NOAA's outlooks are probability statements, not promises. A below-average or suppressed season can still contain a damaging storm if one system finds a window of lower shear, strong moisture, and warm water. The Gulf, Caribbean, and Western Atlantic do not need a busy season to produce one dangerous landfall. They only need one favorable interval. This is the uncomfortable arithmetic of hurricane risk. People experience storms one at a time. Seasonal forecasts describe many storms across months. The difference between those two scales is enormous. A season can be statistically quiet and personally catastrophic. A basin can be mostly hostile and briefly permissive. A coastline can go weeks without a disturbance and then face one storm that matters. The Eastern Pacific demonstrates the same point in reverse. A system does not need a major hurricane label to expose people. Tropical Depression. 2E near southern Mexico carried a modest wind forecast, but its rainfall forecast included heavy totals over steep terrain. The Central American disturbance carried flooding concerns regardless of whether it became a tropical cyclone. These were not contradictions of the forecast. They were reminders that different hazards mature on different timelines. The public map privileges the dramatic object. A named storm receives attention. A cone receives attention. A Category 4 receives attention. But tropical danger also exists in broad low pressure, deep moisture, slow movement, saturated soils, mountain slopes, and river basins waiting below cloud cover. Those things do not always produce a clean headline. They produce consequences. A quiet Atlantic can therefore create two kinds of false comfort. The first is geographic, assuming the lack of Atlantic development means the wider tropics are calm. The second is categorical, assuming that if no major hurricane exists, no major hazard exists. Both errors were visible in the early June setup. The Atlantic had no expected formation. The Eastern Pacific had active systems. The wind categories were low. The rainfall risks were real. Meteorologists separate these layers because they have to. One product addresses formation probability. Another addresses track. Another addresses wind. Another addresses rainfall. Another addresses flooding. Emergency managers then translate those layers into roads, shelters, power crews, drainage systems, port operations, and evacuation decisions. The public often receives only the simplified image. That image can be correct and still fail to carry the full risk. The Atlantic's silence was real. It was also narrow. The ocean south of Mexico was not silent. The air above Central America was not empty. The developing El Niño signal had not shut the tropics down. It had shifted the problem into places where the first danger was not a catastrophic eye wall, but water moving through vulnerable terrain. That is why the absence of a storm marker should never be mistaken for the absence of a storm environment. The map may be blank in one basin while another basin is beginning to organize. The category may be low while rainfall becomes dangerous. The forecast may be accurate while the public lesson drawn from it is wrong. A quiet Atlantic is useful information. It is not immunity. The season that tests the shield. The season does not begin with a storm. It begins with a comparison. One ocean is watched because history taught people to fear it. Another ocean is active because the atmosphere has already given it permission. Between them sits the phrase that made the early forecasts sound safer than they really were: El Niño protection. The phrase is not wrong, it is incomplete. In the Atlantic, El Niño often strengthens vertical wind shear across the Caribbean and tropical Atlantic. That shear disrupts developing storms by tilting their thunderstorm columns away from their low-level centers. It makes it harder for tropical waves to build the stacked, warm core structure required for hurricane intensification. This is why El Niño years are frequently associated with reduced Atlantic hurricane activity. But the same climate pattern can also make the eastern and central Pacific more favorable for tropical cyclones. The shield over one basin can become an opening over another. That was the early June pattern in its simplest form. The Atlantic map was blank. The National Hurricane Center stated that there were no tropical cyclones in the Atlantic at that time. No Atlantic Category 4 hurricane was forming inside 72 hours. No tropical cyclone development was expected on the visible Atlantic outlook. For viewers focused only on the basin that threatens the United States most visibly, the map looked calm. Across the continent's other tropical boundary, the same agency was issuing advisories for the Eastern Pacific. Tropical depression. 2E was near the southern coast of Mexico, with maximum sustained winds near 35 miles per hour, moving slowly northeast. Tropical depression. Amanda was farther west, also being monitored. The Eastern Pacific had the activity. The Atlantic had silence. That contrast was the real signal. 2E was never the monster implied by the strongest headlines. It lacked a well-defined inner core. Its low-level center was elongated. Convective banding was limited. The National Hurricane Center discussion noted very warm sea surface temperatures greater than 30 degrees Celsius and a moist air mass, but also said rapid intensification was not likely during the next 24 hours. The official forecast showed only moderate strengthening before inland weakening and dissipation. Yet the storm still mattered. Its key message was not built around wind. Heavy rainfall was expected over portions of southern Mexico, with life-threatening flooding and mudslides possible, especially in areas of steep terrain. Tropical storm conditions were expected along the coast, but the more consequential threat was water falling over mountains, entering rivers, loosening soil, and turning roads into channels. The system was weak by category logic and serious by terrain logic. This is where the season tests the shield, not by producing the most dramatic storm immediately, but by revealing how fragile the public interpretation of protection can be. Protection from what? In which basin? For how long? Against wind or against rain? Against named storms or against tropical moisture? Against seasonal totals or against a single bad landfall? The Climate Prediction Center's May 14 discussion made the uncertainty explicit. ENSO neutral conditions were still present, but El Niño was likely to emerge soon, with an 82% chance during May through July and a 96% chance of continuing through the northern hemisphere winter. Confidence in El Niño's occurrence had increased, but there was still substantial uncertainty in peak strength, and the strongest events require significant ocean atmosphere coupling through summer. That is not the language of an impenetrable shield. It is the language of a developing climate signal. A mature El Niño can strongly influence hurricane patterns, but the early season atmosphere does not always wait for the seasonal label to settle. The ocean can warm before the winds fully respond. The Pacific can become active before Atlantic suppression is complete. A quiet week can occur for the right reason and still tell only part of the story. Seasonal climate does not erase weather. It changes the odds under which weather operates. The old way of reading a hurricane season is too narrow for this pattern. Count the named storms. Watch the Atlantic, wait for a cone. Rank the category. Measure the season by the biggest eye on the satellite. That method misses the storm that fails to become powerful, but sends 12 inches of rain into steep terrain. It misses the broad, low-pressure area that floods before it is named. It misses the Pacific Basin because the Atlantic headline was quiet. A better reading begins with the environment. Where's the shear? Where's the ocean heat? Where's the moisture pooling? Which basin is favored? Which coast has mountains close to warm water? Which disturbance is slow enough to let rainfall accumulate? Which forecast product is describing wind, and which one is describing impact? The atmosphere had not contradicted science. It had contradicted the shortcut. El Niño can suppress Atlantic hurricanes and still leave the eastern Pacific exposed. It can make one season below normal and still allow one damaging storm. It can reduce the probability of intense Atlantic activity while another coastline faces flooding from a weaker cyclone. Those statements can all be true at the same time. That is the final lesson hidden inside the early advisories. The absence of a Category 4 did not mean the threat was imaginary. It meant the threat had been misnamed. The verified hazard was not a major Atlantic hurricane forming within 72 hours. It was an active Eastern Pacific, a developing El Niño background, very warm coastal water, slow-moving systems, and rainfall directed toward terrain that does not forgive long-duration tropical moisture. A hurricane season is not a single scoreboard. It is a moving set of atmospheric negotiations. The Pacific and Atlantic do not respond identically. The ocean and atmosphere do not couple instantly. Forecast maps do not all answer the same question. Categories do not measure every danger. A blank basin can be truthful and still incomplete. The shield exists, but it has edges. It has timing. It has blind spots. It protects unevenly and only against certain kinds of storms. On the wrong coast, under the wrong rain band, the word protection can become the most misleading word in the forecast. The Atlantic may look quiet, but the pattern is not finished. El Niño did not remove the danger. It moved it, reshaped it, and made it easier to misunderstand. The real warning was never just about a Category 4 storm. It was about warm water, shifting wind, rainfall, terrain, and the false comfort of a blank map. If you want more videos like this, subscribe, like the video, and comment where you're watching from. Because the next warning may not look dangerous at first,